Welcome. So I'm just going to show you how you might set up the gears in Autodesk Inventor. So during the tutorial session we kind of ran out of time and I didn't really get a chance to go over the settings and how to set up to do your gears at all really. So I do apologize about that. So here's a video which you can then watch as many times as you want and get an idea of how to do it. Now we need to first of all set up an assembly, so you can either go into advanced and choose a metric assembly template such as standard millimeters IAM, or you could choose, is there an ISO? Do you think that is? Yeah, so you get the idea. The other way you can do it is when we're back in the basic setting, is to go on the settings here to configure the defaults. So I'm going to have millimeters and ISO. They're my default settings. Okay, so that's fine. Then hopefully, and we'll find out in a minute whether this works or not, when I go to new assembly, hopefully it will set up a metric assembly for me. But we'll know in a minute, won't we, whether this is going to work or not. But we'll find out. Before we do putting the gears in, we need to save this. So I'm going to save this in EDT 2019-20. Let me just check where that is. Yeah, it's on my D drive. Then I can always move it later. I'd set up a whole folder really, don't I? So let's go new folder, and this could be my Inventor parts and assembly. So it's all in there. We're going to call this gear test 1. Go save. So we set up an assembly. Next thing we can do then is to chuck some gears in there. So design, spur gear. Now a lot of people were getting confused on this yesterday, on setting up for center distance, ratios and everything else. Now the problem is that if your box looks like that, there's very little information there to then make sure everything's set up properly. So you need to click on the little chevrons here, click on the little chevrons here, and click on this extra set of chevrons here. Okay, now my desired gear ratio, if I can find my Excel spreadsheet, here's my specification. There we go. And so it's still zoomed in from the other day, so let's just zoom that out a little bit. So my power is 2000 watts, RPM 1600 in, 2700 out. There's my rotational velocity in radians per second. There's my gear ratio, roughly 1.7. And these are my teeth options that I could have. Now I recommend just using 17 as the output and this one here is the input. Now to put the ratio into Inventor, this is the ratio. This is called the velocity ratio. So that's speed to speed, 1.6. It's 1.6, so 1.7 roughly faster than coming out. Now we need to do the gear ratio, which is kind of like the opposite. So it's 1 over whatever that value is. So my velocity ratio is roughly 1.7 and my gear ratio is roughly 0.6. So that's what I'm going to use. I'm going to use 0.6 and I'm going to try to set it up so I've got 17 teeth on the output, and then we'll see what the real ratio is later. Okay, so there's my specification. Let's drag that back out of the way. So we reckon 0.7, sorry, 0.6, what am I talking about? 0.6 on here. Now you need to set this design guide up for center distance, because it's going to calculate the center distance between the gears based upon all the information that we enter. And it's also going to check that those gears can carry the load that they need to carry based upon all the information we put in and the materials that we choose for our gears. So at the moment I've got a 0.6 ratio. The module, that's the size of the teeth. Okay, so basically it looks at the number of teeth and the diameter of the gear, the basic diameter of the gear. That's this here, D. That's the pitch diameter. Okay, and so it takes the pitch diameter, divides it by the number of teeth to give you the module. But in reality, what we do is we set the module and we set the number of teeth, and that gives you the diameter. Okay, so we don't necessarily start with a diameter, we end up with a diameter, and that diameter is based upon the number of teeth and the module. So if we have a number of teeth 20 and a module of 2.5, we're going to end up with a pitch diameter of 50 millimeters. Right, so I'm going to set up with a module of 2.5, 20 teeth on the input, and I'm going to go calculate. Oh no, it's disaster. I've gone down to 12 teeth on the output and it doesn't like it. It's not enough teeth. Okay, we could set a correction factor on there, an X correction factor, where we undercut the teeth. But the trouble is, if you undercut the teeth, then you're weakening the tooth and therefore the load carrying capacity is reduced. So it's probably not a good idea. So let's increase our number of teeth on the output. And I know if I look in my calculations earlier, for 17 teeth I need roughly 29 teeth on the input. So I'll have 29 to 17 on this set here. 29 to 17 will give me roughly that ratio, and it's always an approximation when it comes to ratios on gears. So we think we need 29, and now when I calculate, I've now got 17, so 29 to 17. So my diameter is 72.5. My outside diameter is 77.5, and my root diameter is 66.25. Okay, so it's quite a large gear. And the output gear, again, this goes from 48 to 36, but the base diameter is, the pitch diameter is 42.5. So that's this one here. So this gear works. It's a little bit larger than I'd like in physical size in the diameter, but we also need to make sure that our pitch diameter is more than the face width as well. Okay, so the face width, that's how long each tooth is going across the gear. So we might come back and change this module and use a smaller module. If we use a smaller module, we end up with a smaller diameter gear. Okay, so if we imagine this is 29 times 2.5, you end up with 72.5, don't you? If this was 2, a module of 2, we'd end up with 58 as a diameter. And you can reduce the module as much as you like, within reason. Let's have a look at the calculation side. Oh, if you're having trouble putting in gear ratio information, just make sure you've got it here set up for input type gear ratio. And the size type needs to be set to module. Okay. Now if you want to put the teeth directly in instead of a ratio, all you have to do is swap it here. then you can input the teeth that you actually want to use. But in this case, so here we've got number of teeth, 29, 17. Let's go calculate. And it gives you the real gear ratio. Okay, 29 to 17. And you can do that if you want to. Let's go to calculation. At the moment, I've put some materials in there. Let's get rid of those. And let's put some other factors in. First of all, let's look at the loads. We've got a power, a speed, and the torque is calculated from it. You can, down the bottom, down here, you can set it so that you're looking at torque and speed, and it will calculate the power. I originally gave you the power and the speed. So let's use that then. So in my example, I'm going to use 2000 watts, 1600 RPM on the input. The ratio will then calculate my real output. So 2000 watts, don't put 2000 kilowatts, 2000 watts and 1600 RPM. There we go. If we go calculate, it's giving us the torque on the input, the torque on the output, the speed on the output. Okay, the efficiency gives you the output power. If you set that efficiency to 1, then obviously the output power is the same as the input power. Now we need to set up some materials. So let's have a look. We don't want to use ANSI, that's US materials. We could either use ISO materials or we could use British standard materials. It's completely up to you. Okay, but you need to make sure that you are looking at this value here, contact fatigue limit, and this one here, the bending fatigue limit, because generally those are the two things that will affect the performance characteristics of your materials in those gears. We also have over here tensile strength, and we have here the yield strength. Okay, what we're really interested in the tensile strength, isn't it? So this here is your fatigue limit, this here is your bending limit. So let's have a look. What have we got? I'm going to go with some... Ooh, such a big decision, isn't it? Let's go with some of these BS80 steels. These should be fine. So let's try one of these. So we're going to go with BS80 M50. And foolishly, I'm going to use the same one on there. So BS80 M50. So on the previous one, I went for face hardened. What shall I have? Yes, I'll use the same one. There we go. So there's our two materials added. Now we can do a quick check, and we see that these have not failed. Normally you get a failure in here, SH, and also the SHST, the safety static safety in contact. Those two values. Okay, those are the ones where normally the materials give you a failure. Okay, So we're okay with those materials. Let's go in here, accuracy. Now this is the grade of the gear. Okay. So you can get a whole range of grades of gear going all the way from, it's either 0 or 1, all the way up to about 12. And as they go up from 0 is the highest precision, and 11 or 12 is the lowest precision. So if you imagine like a piece of agricultural equipment or some mining equipment, those gears are probably not manufactured with super high precision. But if you imagine machine tools, such as like a multi-axis milling machine or something, the gears in there are going to be manufactured to a very high precision. Generally speaking, we use, for general engineering, you might use something from between 5 and 9. Okay. Now, if you can get away with a less accurate gear, like a grade 8, and still have it pass, then that's a good thing, because they need less accurate location as well. But the limiting factor is often how fast those gears are spinning. Because if those gears are not manufactured with high-speed gears, if the gears are not manufactured accurately, you'll get a lot of vibration, and with vibration you get a lot of wear. So you need to watch out for that. If we take this accuracy grade up to, let's say, 12, this may well cause a problem. Yes, so it's now caused a problem. Okay, because we can't guarantee the accuracy of the gear is accurate enough to be able to carry the loads that we need. So we can't use a grade like that, okay, for those sizes. So let's drop this back down, and I'm going to go with a grade of 6 or 7 is fine. Okay. Now this makes a big difference later also when we're setting up the tolerances, because it means that the higher the accuracy, the more accurately those gears have to be located to each other. So that's another factor. So I'm going to go with a grade 6 for now. I'm going to go calculate, and we're well within inside of our specification. You can also set your required life, durability. If you want a gearbox that only needs 100 hours of operation, you might think, oh, that's not very much. But if you imagine a drill that you might use at home or something like that, how many hours is it actually being used at that full load? It's probably not, is it? It's probably each time to drill one hole takes you what, a minute? So it's under load for 1 minute. You might do 60 holes in a year, so that's 1 hour a year. How many years are you going to use this electric drill for? You're not going to use it for a century, are you? So what, 20 years? So you might only need 20 hours of life on it. But generally we design industrial gearboxes for around about 10,000 hours. Okay, but it depends upon the application. But in this case, I'm going to leave it at 10,000 hours. So I'll recalculate just to make sure I haven't done anything weird. Okay, so I'm happy with everything about that gear. But let's have a look, see if I can reduce the size of my gears and therefore the material costs based on those materials that I've chosen by reducing the module. If I reduce the module to 2, you'll see this dimension here for my largest gear, and of course for the other gear, reduce. So it's now down to 58 millimeters and 34 millimeters. That's nice. And it still passes my tests here. Let's try a module of 1.75. Calculate. It's still passing. That's nice. Module of 1.5. Calculate. Okay, so it's still passing. So we now got quite a small module on this, but of course with a small module you get problems of maintaining an effective mesh between the gears. So it's something to watch out for. Let's see if I reduce my module even further. Some of you might have to increase your modules. So now it's failed, you see. Calculation indicates design failure. So let's have a look. So those materials on those loads on those sizes are only good if I bring that back up to 1.5. Of course I could change the materials and get the sizes down, but you then have to look at this number here, DF. This is only 21.75 millimeters, so that's the root of the tooth. So if that's sat on, let's say, a 15mm drive shaft, I've only got 3 millimeters of material either side of that drive shaft, and the tooth could crack. So it's quite worrying being quite this small. Okay, so I'm going to take that up to a module of 1.75, recalculate, and that's more manageable. Okay, so I'm going to have at least 10mm either side, even on a drive shaft of 15 millimeters in diameter. Okay, of course I don't know exactly what diameter of drive shaft I need, but it's a good ballpark figure to think about. So there's my gears. Before I click OK, I'm just going to go into here where it says gear 1, no model, and I'm going to say yes please, I'll have the component, and yes please, I'll have the component. We calculate, and the next thing we need to do, we need to write down the key pieces of information. You need DA. So I'm going to get my spreadsheet over. There we go. So I've got my spreadsheet. Key information. This is for the gears. Okay, so we've got first gear and second gear. Now the smallest of the gears is called a pinion. Okay, so we've got G1 and P1. Okay, so G1, that's my gear input, and the pinion is the output. Or have I got that the wrong way around? No, I think that's right. I hope. Right, so my gear on the input is bigger than the pinion on the output. Brilliant. So we want our number of teeth. Sometimes it's N, sometimes it's Z. So the number of teeth, how many teeth have we got? We've got 29 into 17. So 29, 17. Face width. .30 and 30. Of course you can narrow the face width on your gear, see if that will reduce the material content, and recalculate. It's up to you how you do this. So I'm going to stick with my 30mm face width. Just make sure that my face width does not exceed my diameter. It does. It exceeds my pitch diameter. So I need to reduce my face widths. 28, 28, recalculate, we're still okay. Right, so I'm going to use a face width of 28. So I'll go and find my calculation again. So face width, 28 by 28. M for module, so that's the size of the teeth, so I need my module, and my module is 1.75. And of course it's the same for both gears. You can't have different teeth sizes on the two gears because it won't work. Right, that's the modules. The next specifications we need are DA, D, and DF. So DA is the outside diameter. D that's the pitch diameter. If you imagine you've got two circles marking out the pitch circle of the gears, and you can look this up in the books that I've told you to look up, where those two circles touch, that's the pitch diameter. That's the pitch line. 50.75, and the other one is 29.75. And then DF, that's your root diameter. So that's the bottom of the teeth. Right, that's my geometry done. We need to put our grade. I think did I use a grade 6 or grade 7? I can't remember. Let's have a look. Let's just pop that over there. Accuracy, I used a grade 6. Okay. So we used a grade 6. Now we need to know how these gears act when they're in operation. So we need to know how much force there is pushing the gears apart when they're under load. That's FR, force radial. Or as they say in France, force radiale. Right, so we've got 171.215. And that's in newtons, isn't it? So that's our radial force. And we've also got our torque, haven't we? So we need to think about the torque that we've got on those gears. So here's our torque. It says 11.937. Round up to 12. And the other one will round up to 7 Newton meters. Right, I think that is pretty close to it, apart from one thing. We haven't written down the center distance. 40.25. Okay, and that is distance A. So A is the center distance. So A, and that is 40.25. Right, so there's my specifications. Now, if you click on preview, it gives you information about the gears. All that information's in there as well. So there's gear 1, DA, D, DF. This is a width. If you were to measure across 4 teeth with a vernier, that's what you should get. If you measure between balls, so normally you put a ball or a roller in the gear teeth each side. In this case it's a 3mm roller either side, and you measure across with a vernier, and that's the number that you should get. Okay, it says between wires, but you know, you put rollers in there and it's fine. There's all those values. Teeth mesh, see this angle? So this is the base diameter, the angle between them, that's the pressure angle. Okay, and that there, the pressure angle, where they first come into contact, going through the center line there and across, that sets out the pitch, the base diameter, that's your pressure angle. So it's the angle at which the pressure is applied between the teeth. And most gears, that's 20 degrees. And as you can see up here, pressure angle 20 degrees. And most gears are manufactured with a pressure angle of 20 degrees. So if you've got a tangential force, in other words, the force on the tooth going in this direction, okay, being applied by the torque. So it's the force being applied at a distance is your torque, isn't it? That force has horizontal and vertical components, doesn't it? Okay, and those horizontal components are your torque. The vertical components are your force radial, and your resultant is this here, which is your force along the pressure angle. Okay, so that's everything about setting up to make the gears. You can then hopefully, and I hope this works, click OK. This is going to create these gears. So this is where they're all going to be. So just make sure you notice where they're going to go, and you click OK, and it's making those gears, chucking them all in the hopefully into Inventor. Here we go. So there's my gears. Okay. Once I've done that, I'm just going to save those. Yep. Save and all its dependents. And then later on I can pull those out of SolidWorks. Now how do I... Oh, this doesn't work like that, does it? It's nothing like SolidWorks. So there's my gears. Okay, so I've made my gears. I'll probably take those files into SolidWorks to then chuck holes through them, stick them on a shaft, Bob's your uncle. Okay, or you can use that information that you've just identified and recorded in your spreadsheet to create gears in SolidWorks. And that's that bit of creating the gears.